All right, everybody. So welcome back. Today we're going to talk about systems of linear equations in three variables. So now there will be maybe three equations and three variables. Oh gosh. So first here, they want to start us off light. So our solutions will be triples now, an x value, a y value, and a z value. So they ask us to determine if the triple 5, 3, and -2 is a solution to this system here, where we have 2x plus 5y minus z equals to 27, 4x minus y minus 2z equals to 21, and 5x plus 3z equals to 19. So what we will do is put in 5 for x, 3 for y, and -2 for z, and see what happens. The first equation becomes 2 times 5 plus 5 times 3 minus -2, which equals to, let's see, 10 plus 15 plus 2, which is in fact 27. The next equation becomes 4 times 5 minus 3 minus 2 times -2, which becomes 20 minus 3 plus 4, which is in fact 21. And the last equation that has no y's in it just becomes 5 times 5 plus 3 times -2, which is 25 minus 6, which is in fact 19. So this triple of x, y, and z is a simultaneous solution to all three of these equations. So yes, it is a solution to this system of equations. Okay, so then let's see one in action now. How do you solve one from scratch? So we're going to make heavy use of substitution in this section because I think it's probably the cleanest way that we have right now to solve systems of three equations in three variables. So I have here these three equations, and one thing that I like very much about the second one of these equations is that it has x with a coefficient of just -1 out front. Well, I could rearrange this one and bring x over to the other side and bring -1 over with 2y and 3z and rewrite this equation to be x equals to 2y plus 3z minus 1. I like that because now it will be easy for me to substitute this in for x into the other two equations. If I do that, if I substitute this for x into the first equation and into the third equation, then I will be left with just two equations that are both equations with just two variables, y and z, in them. This then will reduce the problem to something from, say, the previous section. So if I let x equal to 2y plus 3z minus 1, then equation 1 becomes 3 times the quantity 2y plus 3z minus 1 plus 4y plus z equals to 7. And the third equation becomes 6 times the quantity 2y plus 3z minus 1 plus 5y plus 9z equals to -9. Okay, so then let's multiply everything out and see what's going on here. The first equation then becomes something like 6y plus 9z minus 3 plus 4y plus z equals 7. And this one simplifies to just 10y plus 10z equals 10. Okay, the second equation becomes something like 12y plus 18z minus 6 plus 5y plus 9z equals to -9. And this guy simplifies to 17y plus 27z equals to -3. Now, I can take of these new equations here, I can take the first one and divide both sides by 10. That gives me y plus z equals to 1, which I can then solve for z, or I could solve for y. At this point, it doesn't really matter. I'm going to solve for z. So z equals to 1 minus y. Ah, very clever. Now I can substitute this into the other equation and solve for y. So if we have 17y plus 27z equals to -3, I'll substitute in z equals to 1 minus y and get 17y plus 27 times 1 minus y equals to -3. let's see what happens here. We have 17y and minus 27y on this side. That gives us minus 10y. And then we also have plus 27 times 1 equals to minus 3. Then we can subtract 27 from both sides. We have minus 10y equals minus 30. And thus y must equal to 3 after dividing both sides by minus 10. But now that we have y, now we can begin to go backwards and unpack to get z and then get x. So if y equals to 3, then z, which I know is 1 minus y, must be 1 minus 3, alias minus 2. And then back at the beginning, we substituted, we found x was 2y plus 3z minus 1. Well, now I know y and z, so I can solve for x. X will be 2 times 3 plus 3 times minus 2 minus 1, which gives us what? 6 minus 1, which is minus 1. So then the solution is the triple x equals to minus 1, y equals to 3, and z equals to minus 2. Now, I know that might feel like it was kind of haphazard. Like, how did we know to solve for x first? Well, we kind of didn't, but we really just had that, you know, it was easy to solve for x first. So that was why that choice got made there. In these kind of solving systems of 3 equations and 3 variables by substitution, you kind of just want to do like whatever's clever and involves the least amount of division and the least amount of sort of fractions getting involved or anything like that. And you just substitute away until you are able to solve for just one of the variables by itself, and then you can go back using the substitution equations that you made before to solve for the other variables. So let's see another one in action here. So they give us this system of equations where we have 9x minus 2y minus 12z equals 211. 2x minus y minus z equals to 3. And 3x minus 2y equals to 5. So just to show you that you didn't have to always pick the sort of cleanest way to go. So if I was to pick the cleanest way to go, I'd probably solve this second equation for one of the variables there. But I'm going to make a different choice this time, just to, you know, kind of showcase to you that there is definitely more than one correct way to go about doing these guys. So I'm going to take this third equation that has the fewest number of variables in it and solve for y there. So we'll have 2y is 3x minus 5, and thus dividing by 2, we get y equals to 3/2 x minus 5/2. And we will substitute this guy back into equations 1 and 2. So then that first equation becomes 9x minus 2y is 3x minus 5, so I'll put that quantity there, minus 12z equals to 11. The second equation becomes 2x minus 3/2 x minus 5/2, or really minus the quantity 3/2 x minus 5/2, minus z equals to 3. So now we can do like we did before and kind of just expand these out and then simplify and combine like all the like terms and everything. And so the first equation becomes 9x minus 3x plus 5 minus 12z equals to 11, which simplifies to 6x minus 12z equals to 6. And the second equation becomes 2x minus 3/2 x plus 5/2 minus z equals to 3. And that one simplifies to 1/2 x minus z equals to 1/2. Okay, now looking at this equation, we can solve for z. And we can write z is 1/2 x minus 1/2. Now plug this one back into the equation above it, and what do we get? We get 6x minus 12 times 1/2 x minus 1/2 equals to 6. So let's see what's going on there. This gives us 6x minus 6x plus 6 equals to 6. So that just says 6 equals to 6. But we definitely know that's always true, right? And so notice that if we multiply this second equation here, 1/2 x minus z equals to 1/2, by 12 on both sides, we get the original equation above it. Oh, so this is one of those instances where now that we've reduced our system of equations by solving for y in terms of x, we were able to reduce this system of equations to one that was just two equations and two variables, right? And this was one of those types, though, where it was really the same equation just repeated, looking a little bit different because we scaled it by some number on both sides. But really, these two equations are the same equation. They represent the same line. So we're going to have an instance here where we have an infinite number of solutions. So, so we have here that we must have that z is 1/2 x minus 1/2. And we also have that y is equal to 3/2 x minus 5/2. But we have not been able to produce any restrictions on what x has to be. And in fact, x is free to be anything that we want it to be. So you can let x be any real number, and from there, you'll get that z has to be 1/2 x minus 1/2, and y has to be 3/2 x minus 5/2. So our solutions here are now the set of triples where x is any real number, and then for that x, y is 3/2 x minus 5/2, and z is 1/2 x minus 1/2. So that's a little bit more awkward there. So we'll probably talk about that more when we're in class. So come back for the next video. We'll do a couple more examples on this front that are a little bit more application based. So that'll be fun.